Chapter 4, Reactions in Aqueous Solutions, Lesson 3. So this lesson is all about oxidation reduction reactions, which occur when we have a transfer of electrons from one atom to another. So here we're showing a magnesium strip being burned. So this is a combustion reaction, and magnesium is becoming a +2, oxygen is becoming a -2, and it is forming the ionic compound magnesium oxide. So when magnesium is oxidized, it is giving up electrons, which we call oxidation. When oxygen is accepting electrons, we call that reduction. So overall, what is happening here is that there's a total of 4 electrons being transferred between magnesium and oxygen. So you cannot have oxidation without reduction because something has to give up the electrons and something has to accept the electrons. The overall balanced equation, if we take out the electrons, what is actually happening is we have magnesium combusting in oxygen and forming magnesium oxide. So in writing redox equations, we can talk about a couple different things. So one is the reducing agent, and this is the substance that has the power to reduce something else. So if you're the reducing agent, it means that you yourself are being oxidized. Conversely to that, if you are the oxidizing agent, then you have the power to oxidize something else. So that means that you yourself are being reduced. Oxidation is the loss of electrons, and we can also see that as an increase in your oxidation number or increase in your charge. Reduction is the gaining of electrons, so that means that your charge will go down. So in order to figure this out, we have to look at our oxidation numbers, or what we call an oxidation state. So here we see that this is a single replacement reaction. So zinc is replacing copper. So zinc plus copper 2 sulfate gives us zinc 2 sulfate plus copper. So we need to recognize what are the charges on these substances and what's happening. So we can look at another single displacement and see that copper can replace silver and silver nitrate to form copper 2 nitrate and solid silver. So in order to figure out what's being oxidized and what's being reduced, we have to have some rules as to how we assign oxidation numbers. So this first line here with oxygen, nickel, bromine, and cobalt, anytime something is in its elemental form, which means it's not bonded to anything else. So we see oxygen is bonded to itself, bromine is bonded to itself, but these are diatomic elements. So your oxidation number is always 0 when you are in your elemental state. I like to call these standalone metals as well. So if you see a metal all by itself with a solid symbol after it, or perhaps mercury that is a liquid, but when you're not bonded to anything else, you don't take a charge. So number 2, we have magnesium oxide, we have sodium bromide. So when you're looking at main group elements, which we've talked about before, we can go off of their group numbers and figure out what their standard charges are. We know magnesium is a group 2, so it's a +2. Oxygen is a group 6, it's a -2. Sodium is a group 1 metal, so it's a +1. Bromine is a halogen, which is group 7, so we know it's a -1. Now here in line 3, we're talking about what are the different oxidation states that hydrogen can have. So in these first 2 examples, when hydrogen is bonded to another nonmetal, it is going to be a +1. When hydrogen is bonded to a metal, it is going to be a -1. Now, oxygen, here we're looking at oxygen, is typically a -2, so that's the oxidation state in water. It's what it is in carbon dioxide. However, we have what's called the peroxide ion, where it is an O2 with a -2 charge. So effectively, each oxygen atom has a -1 charge associated with it. In line 5, we're looking at all fluorine. So all compounds that contain fluorine in them, fluorine will always be a -1, no matter what. Now here we have iodine showing up in 3 different ways. So typically iodine, because it is a group 7, if it is bonded to another main group element or just one single metal, iodine is going to be -1. However, the oxidation state can change. And in order to do that, we look at setting up our charges on the things that we know. And this compound overall has a charge of 0. It is neutral because there's no charge up here. So if we know that oxygen is -2, we have 2 of them. That means that oxygen is contributing a -4. We know that sodium is always a +1. So we take the difference there of -4 plus 1 is a -3, which means that iodine here actually has to be a +3 in order to be balanced. Here we have IF7, iodine heptafluoride. Fluorine is always a -1. There are 7 of them, so 7 times -1 is 7. It is a neutral compound, so iodine has to be the opposite in charge, which means that iodine is a +7. Down here, we're looking at polyatomic ions. So here, where we set our equation effectively equal to 0 to find our charges, well, now you have to set your equation equal to the charge. So I know that oxygen is a -2. There's 4 of them. So 4 times -2 is -8. Something plus -8 has to equal -2. That means chromium here is a +6. We can do the same thing here with the dichromate. Oxygen's -2, 7 times -2 is -14. 2 times chromium has to equal, or 2 times whatever the state of chromium is, plus a -14 has to equal -2, so chromium once again is a +6. Oxygen is a -2. 3 times a -2 is -6, so something plus -6 equals -1, which makes nitrogen a +5. Once again, oxygen is a -2. 4 times -2 is -8. So something plus -8 has to equal -2, which makes the charge on sulfur +6. So there's rules here. There are rules that are listed in your book. I just went over some of those rules. So as we had stated, fluorine's always a -1. Group 1A and 2A metals are +1 or +2 respectively. Hydrogen is a +1 unless it's with a metal, then it's a -1. Oxygen is almost always a -2, except for when we have the superoxide or the peroxide ion. And group 7A, other than fluorine, is a -1, but can change respectively depending upon what it is bonded with. So in order to figure out oxidation numbers, we're just taking that process which I just described. We always start with the oxidation numbers you know. So in sulfuric acid, we know that oxygen is a -2, hydrogen is a +1. There are 2 hydrogens, so overall it's contributing a +2. There are 4 hydrogens, so overall is contributing a -8. Sulfuric acid is overall a neutral charge, so that means that sulfur has to be a +6 in order to balance out all of our charges. So how about in the chlorate ion? Well, we know that oxygen is a -2, and we know that we have to set this equation equal to -1 because that is the overall charge on it. 3 times -2 is -6, which means that chlorine has to be a +5 because 5 minus 6 is -1. So whenever you're assigning oxidation numbers, you look to what you know to solve for what you don't know, and then it becomes an algebraic equation. So some practice with oxidation numbers and being able to identify what's being oxidized and what's being reduced for a particular reaction. So here we're showing the combination reaction or synthesis of potassium bromide from its elements. So elemental bromine starts at a 0. Elemental potassium starts at a 0. When it becomes a new compound, we look at group numbers and say, all right, well, we know potassium's always a +1. It's a group 1. That makes bromine a -1 because overall this is neutral. So then we look, bromine went from 0 to -1, which means it was reduced. Potassium went from 0 to +1, which means that it is oxidized. So potassium gave up an electron and bromine accepted it. Down here, we were showing a combustion reaction. This is ethanol, and in complete combustion, we're going to produce water and carbon dioxide. So we go through the things that we know. And I'll talk about this in a minute. So we know that oxygen, when it's in its elemental form, is 0. Hydrogen is always a +1 when it's with other nonmetals. Oxygen is a -2. Here, because oxygen is a -2 and we have 2 of them, that makes this contributing a -4 overall. This is a neutral compound, so carbon has to be a +4. So here, right, this looks a little tricky, but if we break this down and just simply look at how many carbons do we have? 1, 2. How many hydrogens do we have? 6. How many oxygens? 1. So we know that this all has to equal 0 because this is a neutral compound. I don't know the charge on carbon because carbon can change. However, because hydrogen is bonded to other nonmetals, it is a +1. Oxygen is a -2 because it's not in any sort of special state. So here we have 6 minus 2 is a +4. There are 2 carbons, which means that each individual carbon has to be a -2 because 2 times -2 is -4, which then allows us to get to an overall neutral charge of 0. So even though the oxygen in this compound is not changing, the oxygen here is. So whenever you're doing combustion reactions, oxygen is always going to be reduced. And if you are combusting hydrocarbons or some type of organic compound, this is ethanol, so it's an alcohol, but your carbon is going to be oxidized because we can see here it went from a -2 to a +4. So that means that it somehow gave up 6 electrons. And when you go through and you were to balance it, then we would show that the oxygen gained those electrons respectively. So just a general overview of the different types of redox reactions. I showed a couple of these on the first slide. So you have a displacement or a single replacement where one thing is replacing something else. So you have what's called hydrogen displacement. So we can often see this times when we dissolve certain metals in acid. Not all metals are able to be dissolved in acid, but we are going to produce hydrogen as a gas. We have metal displacement, so one metal is replacing another metal in a compound. And then we can see halogen displacement, which means that we're replacing halogen in a compound. So all single displacement reactions are redox reactions. Any type of combination reaction or synthesis is also going to be a redox reaction because we're starting with our element and we're becoming an ionic compound here, for example. Decomposition reactions are also going to be redox reactions because oftentimes when we decompose something, we might decompose it into its constituent elements. Here we're showing potassium chlorate decomposing into potassium chloride and oxygen. So what's changing here is oxygen is changing and then the chlorine is changing. So oxygen becomes oxidized and the chlorine becomes reduced. Last type of redox reaction is a combustion reaction. So we know combustion is anytime you have oxygen present as a reactant. That's important, not as a product. So you can combust nonmetals, which when we did the copper sulfide lab, we saw that we created this blue flame when we were burning sulfur, produced sulfur dioxide. And we can also combust metals. So here we show magnesium becoming magnesium oxide. So the last part of this section is going to deal with the activity series for metals and how can we read this table. So here we have this arrow that says increasing ease of oxidation. So basically that means that lithium is the easiest element to oxidize. It wants to give up its electron, and we see here then potassium is next. Now, in order to have something oxidized, something also has to be reduced. So that means when you look at this table, and if you see one of these elements, but reverse, so Mn2 plus going to Mn, that means that it can oxidize anything above it. So nickel can oxidize anything above it if it's nickel 2 plus, because then that means it's going to accept the electrons because the other substance was oxidizing them. So the important thing in learning how to use this activity series for metals, well, I guess there's hydrogen on here, but you're looking at the location. So anything below can oxidize anything above as long as the equation is written in reverse. So how can we apply this? Predict if the following reactions can occur. If so, write the molecular net ionic equations. So what we're looking at here is iron. It would be oxidized because it's starting as an element. It would be forming the iron 2 ion. Here, platinum is a +2. So platinum is going to be reduced. So platinum to platinum solid, platinum 2 plus to platinum solid. Can that happen? You look at your table, the activity series, and you see that yes, platinum is below iron. If we flip platinum's equation, we see that it has the power to oxidize iron. So we can write that out down here. It is a single displacement, so iron is displacing platinum to form iron 2 chloride, which would be aqueous. We know it's aqueous because our solubility rules tell us so. And then forming platinum as a solid. So our spectator ions would be the 2 chloride ions that get canceled out. And now we have a net ionic equation. I would just like to point out that precipitation reactions and acid-base reactions are never redox reactions because in those you're doing a double displacement, metathesis, exchange, however you want to word that. So here we have solid chromium reacting with gold 3 nitrate. So once again, where is chromium in the activity series table? Where is gold? Well, gold here is the substance that is going from a positive back to its neutral state, so that means that it's being reduced. If we flip that equation around, do we see that gold is underneath chromium in the table? Yes, it is. So this reaction can happen. So chromium replaces gold to form the chromium 3 ion in solution, basically. We're just displacing, and we get gold as a solid. So once again, our 3 nitrates would be our spectator ions. And so then here's our net ionic equation. Can lead replace zinc in zinc sulfate? Well, lead would have to be oxidized. Zinc would have to be reduced. We look at the table and we see that zinc is actually above lead. So that means that this reaction cannot occur as written, and we just write no reaction.